Substitution area between curves. So let's figure out how we can find the area between two curves. So for example, suppose I have a function y equals f of x. We'll call that the upper curve because it's on top. And another function y equals g of x, we'll call that the lower curve because it's on bottom. And suppose we want to find the area between these two curves from the point x equals a until the point x equals b. Alright, if f and g are continuous with f of x greater than or equal to g of x on an interval ab, then the area of the region bounded above by y equals f of x, below by y equals g of x, on the left by the line x equals a, and on the right by the line x equals b, is the integral from a to b of f of x minus g of x. We call A the area of the region between y equals f of x and y equals g of x from A to B. Alright, so let's do an example. Let's find the area of the region between y equals x plus 6 and y equals x squared from 0 to 2. Alright, to do this, we need to determine which one is the top function and which one is the bottom function. And also what our limits of integration are. So it's usually pretty good idea to make a sketch of what's going on. So here's the sketch of y equals x plus 6. Here's a sketch of the curve y equals x squared. We said we were going from 0 to 2. So this is the region we want to find the area of. So here our top function is this one here, x equals 6. X plus 6. And this function here, y equals x squared, is our bottom function. So that gives us that my area is equal to the integral from 0, my leftmost point, to 2, my rightmost point, of the function that's on top, x plus 6, minus the function on bottom, which is x squared. So then you just go ahead, calculate this integral, and you get that your area is equal to 34/3. Alright, let's do another example. Find the area of the region enclosed between the same two functions, y equals x plus 6 and y equals x squared. Alright, in order to do this one, I haven't told you what interval we're doing it on, so we need to figure out where the curves meet. To do that, you set the two equations equal to each other. So you get x squared is equal to x plus 6, and now we'll solve for x. You bring all your terms over to one side so that you get x squared minus x minus 6 is equal to 0. You factor the left-hand side, and that tells you that x will be equal to 3 or x will be equal to negative 2. So now when we do our sketch, we already knew that this line went this way, that y equals x squared looked like this. Now we know they cross here at x equals negative 2 and at x equals 3. So let's go back and look at that picture. So here on this region, our top function is x plus 6. Our bottom function is y equals x squared. Our lower limit of integration is the leftmost point, so that will be here at negative 2, and our upper limit of integration will be the rightmost point that we go to, which is x equals 3. So our area is going to be equal to the integral from negative 2 to 3 of my top function minus my bottom function. We go ahead and evaluate this, and we get that the area is equal to 125/6. Feel free to stop the video at any time and make sure you can do these calculations yourself. Alright, here's another example. Find the area of the region enclosed by the curves y equals the square root of x, y equals negative 6 plus x, and y equals 1. Alright, to do this, let's sketch all the curves and make sure we clearly label any intersecting points. The sketch is going to look like this. Here's the curve y equals the square root of x. Here's the curve y equals negative x plus 6. and here's the curve y equals 1. Once you've drawn these three curves, you should be able to see where they intersect and know that these two intersect at 1, 1, these two intersect at 5, 1, and these two intersect at 4, 2. Now look at the picture. The top function depends where you are on the graph. For x between 1 and 4, the top function is the curve y equals the square root of x, and the bottom function is the curve y equals 1. For x between 4 and 5, the top curve is this one right here, which is the line negative x plus 6, and the bottom curve is the line y equals 1. So when we go to find the area here, we're going to need to break it up into two different pieces, since it has two different top functions depending on where you are. So my first area, we'll call this leftmost point, goes from x equals 1 to x equals 4. So those are our limits of integration. And then it's our top function, which is the square root of x, minus our bottom function, which is y equals 1. If you evaluate this integral, you'll get it's equal to 5/3. Our second area here is the area that runs from x equals 4 to x equals 5. So those are our limits of integration. And then our top function is negative x plus 6. And then we subtract off our bottom function, which is the curve y equals 1. When you evaluate this integral, you'll get it's equal to 1/2. So that means our total area is the sum of these two areas, and that gives us 13/6. Now, sometimes you need to find the area of a region that's bounded above and below by horizontal lines and bounded on the left and right by the graphs of two functions. So it's really going to be the same as what we did, except now we're going to switch the roles of x and y. So the limits of integration are going to be from C to D, right? The lowest one to the highest one. And then you're going to have your top function, this one here, the bigger one, and you'll subtract the smaller one, which is the bottom function, which is this one here. So when we do that, let's use that to redo example number 3, but this time integrating with respect to y. So the problem was find the area of the region enclosed by the curves y equals the square root of x, y equals negative x plus 6, and y equals 1. All right. So the way we're going to do this, we want to integrate with respect to y instead of x. So that means we need to rewrite all our equations so that it's x equals some function of y. So the line y equals negative x plus 6 becomes x equals negative y plus 6. The equation y equals the square root of x becomes x equals y squared. And now when we integrate, we're going to integrate our y values starting here at 1, and we're going to sum up through 2. So the integral is going to go from 1 to 2 in the y direction. Then we take our top function, which is this one here, so that's x equals negative y plus 6. And then we subtract off the bottom function, which is this one here. So that's x equals y squared. So we subtract off y squared. Now this we just evaluate, and we end up with that's equal to 13/6, which is the same answer we had before. And this was a lot easier to do because we didn't need to break it up into two different integrals. All right, let's do another example. Let's find the area of the region enclosed by the curves y equals x to the 4th minus 4x squared plus 4 and y equals x squared. All right, let's think about this. We know that y equals x squared is a parabola with vertex at the origin and it opens upwards. How about the other function? Y equals x to the 4th minus 4x squared plus 4. Well, I can factor this. This is a perfect square. And then each one of these is a difference of a square. So this tells me that this function crosses the x-axis only at the square root of 2 and negative square root of 2. Alright, and since it's a fourth degree polynomial with a positive leading coefficient, I know that the shape is going to look like a rounded W. Alright, and since the graph only crosses the x-axis at 2 points, they must be the bottom of the W's, because if it crossed the x-axis in another way, we'd have that it either didn't cross the x-axis at all, or it would cross at 4 points, or possibly at 3 points. So it's nice to know what it's going to look like, but this doesn't help us. Where do the two curves intersect? Well, the way to figure it out is you set the two equations equal to each other. You bring all the terms to one side of the equation. You fully factor it. And now you know that they're going to be equal to each other when x is equal to 2, -2, 1, and -1. So let's draw a sketch of what it's going to look like. Here's what our curves are going to look like. This is the fourth degree polynomial here. It looks like this green curve is a W. And then the other one, y equals x squared, is this parabola here. And we said they crossed at -2, -1, 1, and 2. So when we do this, it breaks up, creates three regions that we need to find the area of. There's this one here, this one here, and this one over here. So we're going to need to calculate three different integrals. So my first integral is going to go from -2 to -1, and then my parabola will be my top function, and my fourth degree polynomial will be my bottom function. So let's see that set up. Here it is. It goes from -2 to -1. Here's my top function. I subtract off my bottom function. And then we go ahead and do this calculation. You simplify what's inside for your integrand. You find its antiderivative, and you evaluate it. And I didn't simplify here. We'll just leave the answer like this for now. Now for the next section, which function is on top and which one's on bottom switches. So we switch our order here, and we integrate from -1 to 1. That's that big section in the middle. We simplify the integrand, we find the antiderivative, and then we evaluate it. Now for the last piece, that was the integral from 1 to 2. Again, which functions on top and which on bottom alternates. So we just switch the order here. We simplify the integrand. We find the antiderivative, and then we evaluate it. Now that we have this, we're ready to find the total area. The total area is equal to the area of each of the three parts. We plug in the values we found for those. We simplify our answer, and we get that the answer is 8.